Okay, let's use a power series to approximate this definite integral. So how in the world are we going to do this? Well, what we can first do is let's just ignore the limits of integration and get a power series representation for this integral. Let's start there. So how do we do that? Well, let's think about what the derivatives of this are. And if we just focus on the natural log of 1 plus x squared, so we know that this is equal to, so 1 over 1 plus x squared times the derivative of 1 plus x squared is 2x. So if we can get a power series representation of this, then what we can do is integrate the power series to get the integral of, we'll get the integral of natural log of 1 plus x squared, but that doesn't seem like it's, what's the point of that, right? We're looking for the integral of x times natural log of 1 plus x squared. Well, okay, all we're, if you think about it, all we're trying to do is, if the first step in order to integrate this as a power series is we want to represent this as a power series. Once we do that, then we can integrate that, that power series. Okay, so to do that though, we've got to use like a separate integration process where because the integral of this, which is something we can represent as a power series by matching up with this base geometric series with first term 1 and common ratio x centered at 0, we can match this up and create a power series, then integrate that. And so you'll see how this works as we go. But okay, we can rewrite this as we can take this 2x off to the side, because you can bring x terms outside of the summation as long as they're not tied to an n. And now we've got, so 1 minus okay, and there we go. So if this is g of x, then this is g of minus x squared, right? So we can say that, just plug in minus x squared here, and we've got, so 2x okay. But now we can't integrate this yet. We need to bring this 2x in and clean it up a little bit. So, all right, we've got, so we can take out a minus 1 to the n, then we've got a 2, then we've got an x and an x to the 2n. Okay, minus 1 to the n, and then 2x to the 2n plus 1. Okay, there we go. So now this is a power series representation of this function. But this function is the derivative of this. So, we can think about it like this. You integrate both sides, and what you're left with is, so natural log of 1 plus x squared, that's this integral, is equal to, so now we just need to, how do you integrate a power series? Well, you first take out a c, like that, plus, and then you just go to the x, it's all with respect to x, integrated with respect to x, so everything else is constant. All the n terms are constant. So here it's just going to be x to its power plus 1 divided by that power with the 1 added to it, right? X to the 2n plus 1 over 2n plus 1, and that's it. But you just have to be careful. It's kind of like differentiation. If the x has some stuff in it, the x term, like if you have like 2x raised to all that, then it's like you have to do a substitution. In the same way, like, okay, like if you had 1/2 x to the n, well, what's the derivative of that? it's n 1/2 x to the n minus 1, but then you have to say, okay, the derivative of 1/2 x is 1/2 and add that 1/2 factor. Same thing. What's the integral of this? Well, you can't just say 1/2 x to the n plus 1 over n plus 1. You have to like do a substitution first. Just keep that in mind. But it seems like, wow, this integrating a power series has to be really hard. Look how complicated this is. It's not as hard as it sounds because it's with respect to x. Everything else is constant. All the n's are constant. That's why it's not as hard as it sounds. Okay, so we've got the c, and then you don't have to worry about, potentially with differentiation you eliminate a term. Well, with integration, you don't eliminate terms, right? You add a term. So, okay, the 0 stays the same, the starting point. And then we've got 2n plus 1 plus 1. That's 2n plus 2. So we're going to be dividing by 2n plus 2. Now we have a 2 here, so you can factor out from 2n plus 2. You can factor out a 2, and you're left with just n plus 1. So those 2's cancel. So we've got, right, and then x to the 2n plus 2. Okay, now let's solve for this c, and I don't think I made this clear enough I think it was a couple of videos ago where we found a bunch of power series representations for functions via integration. But when you're solving for c, like when you integrate a power series, you're going to need to know, like, okay, you're gonna set x equal to the, well, you can set it equal to whatever you want, but typically you'll set x equal to the center point of the series. And when I say you can set it equal to whatever you want, the goal is you're trying to set it equal to something so you can get a known value. If you know that when you set x is equal to something, it gives you a value, that's what you want to do. So when x is equal to 0, we can see that we have to be aware of that. So yeah, when x is equal to 0, or the center point, most of the terms go away, but maybe there's a first term left over. That's not multiplying the variable, but that's not the case here. So like, think about the first term, you'll still have an x squared. So when x is equal to 0, this is 0. But to solve for these integrations, in order to solve for the constant, that's not enough, because we need to have like this on the left side here, right? We plug in 0 here, so we get, if this is 0, we get natural log of 1 is equal to c. Well, natural log of 1 is 0, so c is 0. You see what I mean? It might not be clear what I just did there, or like the purpose of what I'm talking about, but like you need to be able to plug in the x to the power series, and that simplifies. And then, but it needs to, okay, so you can't have just c plus a number. Well, what are you going to do with that to solve for c, right? It needs to be then equal to something that you also like plugged x into. So then it's an equation, so you can solve for c. Otherwise, you can't solve for c. Okay, so c is equal to 0. So therefore, okay, so but what are we going to do with this? Yeah, we have natural log of 1 plus x squared represented as a power series, but okay, so what does that help us with? Well, this is what it helps us with. We're going to multiply both sides by x. Now let's simplify this, and we'll have the power series representation for this, which is what we're trying to integrate, and then we can go ahead and integrate that power series. So all right, minus 1. So x to the first times x to the 2n plus 2 is going to be x to the 2n plus 3. Okay, so now we've got this as a power series. We can go ahead and integrate this. And now, but we're doing a definite integral, but what we're going to do is let's go ahead and just get this indefinite integral first. Okay, let's do that. Let's get this indefinite integral first. Okay, so what we're doing is we're doing this. So integrate both sides. And so we get, let's see. So, okay, c plus, and then we've got the integral from, or the sum from n is equal to 0 to infinity of, so x to the 2n plus 3 plus 1, that's 2n plus 4. It's going to be over 2n plus 4. We could factor out that 2 and get 2 times n plus 2. So we'll have 2 times n plus 1 times n plus 2, and then x to the 2n plus 4. Okay? We're doing the definite integral, but we didn't even have to find the c, because for the definite integral, the c doesn't matter. So we could just, just like ignore the c. So all we're thinking about is we're evaluating this from 0 to 0.2. So the idea is you would plug in 0.2 for x, have that as an infinite series, and then subtract that for plugging in 0 for x, that is an infinite series. But every term has an x, so when you plug in 0, this infinite series is 0. So what this ends up being here is this definite integral is this series with x is equal to 0.2. Okay? So, okay, I'll write it here. This is equal to the sum from n is equal to 0 to infinity. So 0.2 is equal to 2/10, that's 1/5. So 2 okay, and then that's it. This is an exact equality here. Pretty cool, right? But the question is that it wants us to, so yeah, we solved that. That's the solution, the exact solution. But it wants us to now estimate this to correct to 6 decimal places. So how do we do that? Well, okay, this is, how do we estimate series? We use the partial sum. So we'd say that we go from n is equal to 0 to, we change infinity to, like we write this like from I is equal to 0 to n. S sub n is equal to this sum from I is equal to 0 to n, and that's the partial sum, and then we pick an n. And the n we pick is based on how accurate we want. And so, okay, well, we want to be accurate to within 6 decimal places. So that gets into the R sub n estimations. Well, this is an alternating series, right? Each term alternates sign. Let's make sure it's alternating. It's truly alternating. Yeah, so everything else is positive, and so you just have this as alternating each term. It's making each term alternate sign, so it's alternating series. Well, alternating series, the R sub n it's actually really nice. You just think about the B sub n of this series as the absolute value of this, and that's the magnitude of the accuracy for the nth term. So this is A sub n, this is A sub n, the B sub n is the absolute value of A sub n, and then what happens is the R sub n is going to be, well, the absolute value of the R sub n, because it's alternating, so this could be above or below the actual value. This is going to be less than or equal to B sub n plus 1. So all we need to do is just plug in n's, like n is equal to 0, 1, 2, into the B sub n, which is just it's this without the minus 1 of the n. And so we get a value that's more, that's smaller than 6 decimal places. And then we know if we do the partial sum up to, I guess it would be the point before that, the answer is going to be that accurate. So, all right, let's see. Let's just type this formula in. So 1/5 to the 2 times n plus 4 divided by 2 times n plus 1 times n plus 2. There's the a sub, or the b sub n, which is all we're concerned about. Store that as e. Well, no, let's store that as b, because we're going to actually make the a sub n. So store that as b. Okay. So we want to say, okay, what is b with n is equal to, let's say, 3. So that's better than 6 decimal places. That's almost better than 6 decimal places, right? It's like 0.1, you know, like this is technically, you're not, if someone says that you're accurate, the absolute value of your accuracy is less than this, then it's not quite, it's almost very close to 6 decimal places, but it's not quite there. So we want to do, so we're going to use this. This is the b sub n plus 1. So this is the b sub n plus 1. That means we want to calculate that partial sum going to 2. So we want to sum n is equal to 0 plus n is equal to 1 plus n is equal to 2. And we'll be accurate to within 6 decimal places. So, all right, there's the b. Now, if we said that b times minus 1 to the n, and we're going to store that as a. Okay, so there's the a sub n. So we want to say a with n is equal to 0 plus, and we want to do a with n is equal to 1 plus a with n is equal to 2, and that's going to be the answer. That's the definite integral accurate to within, you know, it was like whatever that b sub n plus 1 was. At least more than 6 decimal places. So is approximately equal to and then this is accurate to, if we take the b with evaluated with n is equal to 3, it's accurate to within more than 7 decimal places.